The presentation is all about the comparison between Schottky barrier CNT with metallic electrodes and MOSFET-like CNT holding doped electrodes in the context of ballistic transport. So, without further ado, let's get started. Well, in this slide, I will be talking about the outline of this presentation. First, I will define the carbon nanotube, its construction, and the application of it. Next, the field effect transistor using carbon nanotube will be covered. Then, the carbon nanotube field effect transistor modeling and analysis approaches like the non-equilibrium green function (NEGF) approach and the ballistic transport assumption will be discussed. These two approaches were taken due to the minimum amount of iterative method. Then, the findings, the ID versus VDS characteristics of the Schottky barrier CNT and the MOSFET-like CNT will be discussed. I have picked 3 simulators from the NanoHub org to see how these two categories of CNT perform. I changed the Schottky barrier height, chirality, oxide thickness, dielectric constant of the gate oxide substrate, and temperature to see how these two operates, and I have also uh, evaluated the performances of these two categories under the static and dynamic domain. More about carbon nanotube. Here we have a graphene sheet. If we roll it up, constructions of the carbon nanotube can be like these ones. There are several types of carbon nanotubes, such as the single-wall carbon nanotube, double-wall carbon nanotube, and multi-wall carbon nanotube. Upon changing the chirality angle, the chiral vector varies, which leads to the armature, zigzag, and chiral CNTs. Researchers have discovered its outstanding electrical and mechanical properties. They are the extremely low electrical resistance, which results in ballistic transport. Lengths of the carbon nanotube can be as large as hundreds of nanometers. Diameter is small. Valence conduction bands are symmetric. Low power consumption. Carbon nanotubes tensile strength can be as large as the steel uh, in some cases, but the steel's tensile strength is lower than the carbon in most of the cases, and it's truly unimaginable. Researchers of the University of Texas found that carbon nanotubes have special connectivity among themselves, which forms the carbon nanotube forest. This carbon nanotube forest helps out to create the tennis rackets, the bicycle bumpers and frames, and high-end cars body. These are a few applications of carbon nanotubes. I will be talking about the operation of carbon nanotube field effect transistors. To start with, I would like to mention a kind of it, that is the Schottky barrier CNT, which has undoped or metallic electrode. This whole structure can be represented by the electrical model here. The properties of it are like this. The Schottky barrier exists between drain or source and channel. This Schottky barrier can be controlled by the gate bias voltage. At the source channel junction, direct tunneling through SB is evident. Then, after reducing the gate oxide thickness, we can have the ambipolar conduction uh, that is defined by the simultaneous hole and electron conduction, and that leads to the leakage current, which is not good for any operation. Then the MOSFET like CNT FET, which occupies the doped electrodes. This can also be represented by an electrical model shown here. The characteristics of the MOSFET like CNT FET are like this. Firstly, the drain source contacts are heavily doped. Faster switching is possible. Then transistor delays and parasitic capacitances are quite negligible. The ambipolar conduction is controlled in this domain, and the higher on current is evident. In this slide, you can see there are two diagrams which we have covered in the previous slide for the electrical models for the SB CNT FET and the MOSFET like CNT FET. Now I am going to talk about the NEGF approach, which is only applicable for the Schottky barrier CNT FET. The Schottky barrier CNT FET can be represented by a model shown by green, and this green function is only applicable for a point charge which randomly moves, and the Hamiltonian operator in the matrix form will be used in order to represent the ID function, that is the drain current function. So the Poisson equation could also be incorporated in the radial direction, and the NEGF approach will be used by taking into account several parameters as shown here in the iterative way. The iterative calculation can be cumbersome, so we will need a compact model, the ballistic compact model. So here a model is shown, and the bottom three figures could be used to represent the drain current, and the general expression of ID for the first diagram is shown here. Based on this general expression, we can have the ID for the SB-CNT FET and the ID for the MOSFET like CNT FET. As we are considering the Schottky barrier for this one, the complexity of the ID could be much larger, and for this the resultant current would be much lower compared to the MOSFET like CNT FET, as we will be observing in the next slides. For the simulation purpose, I have chosen 3 simulators from NanoHub.org. The reason behind choosing these 3 simulators is I couldn't change the parameters from one simulator, so I looked for other simulators in order to see how the SB CNT FET and MOSFET CNT FET perform. Schottky barrier CNT FET simulator, cylindrical CNTFET MOS simulator, and CNTFET lab were used to simulate the CNTFETs by varying the SB height, oxide thickness, the chirality, temperature, and dielectric constant of the gate oxide substrate. Among these three, I mostly chose the CNTFET lab because it has the capability to change the parameters mostly. So the thing is that the zigzag tube is only possible for the CNTFET lab. The metallic electrode can't be changed using the CNTFET lab. If I choose the armchair and chiral with n of different values, the CNTFET lab will crash. So just zigzag tube was taken into account. Yeah, that's pretty much it from this slide. In order to get the EK diagram, I kept the following parameters constant: the insulator thickness at 4 nanometers, dielectric constant of the titanium pentaoxide, that is the gate oxide substrate, at 22, the temperature at 300 Kelvin, and the drain to source voltage at 0.5 voltage. The variable parameter was only the gate to source voltage, that is 0.1 volts to 0.8 volts. This diagram demonstrates that after changing the VGS from 0.5 to 0.8, the gap between the conduction and the valence band gets increased. That's not a good thing for a normal operation. But in case of the MOSFET like CNTFET, we can easily see that by changing the VGS from 0.1 to 0.7, the energy gap is constant. So the transfer of electrons from valence to conduction band remains almost fixed. So under changing the parameters, the electron conduction is fixed. So that's a good thing for the MOSFET like CNTFET. So we should choose the MOSFET like CNTFET. The same results will be shown in the following slides. In this slide, I will be discussing about the current voltage characteristics of the two CNTFETs by changing the Schottky barrier height. It's worth mentioning here is that Schottky barrier is not present in the MOSFET like CNTFET. So I will simulate that in a regular way. But to see how the SB CNTFET works, I kept the parameters constant like the previous ones, but I fixed the gate voltage here. The variable parameter is the Schottky barrier height that ranges from 0 electron volts to 1 electron volts. The first diagram shows the Schottky barrier performance, Schottky barrier CNTFET performance by changing the Schottky barrier. When no Schottky barrier is evident, that is the 0 electron volt, the ID, the drain current, is maximum, while the Schottky barrier is 1 electron volt, the ID is minimum. The ID saturates at VD is VDS is equal to 0.3 volts. So that's a bad thing, you know. The MOSFET like CNT has been demonstrated here. The MOSFET like CNT gets the chance to have the ID which saturates at 0.28 volts. So comparing these two figures, we can see the drain voltage is much less than much less for the MOSFET like CNT compared to its counterpart, and the ID is much larger for the MOSFET like CNT as there is no Schottky barrier in it. So it's a good thing to pick the MOSFET like CNT for the complementary applications. By varying the oxide thickness, we can have the current voltage characteristics of these two CNT FETs with the parameters uh, dielectric constant, temperature, VDS, VDG, and the zigzag tube constant, and the insulator thickness uh, variable. We can have the simulation results like this ones. And the first diagram shows that the Schottky barrier CNT FET has the ID, that is the drain current, much lower for the oxide thickness of 10 nanometers, while its maximum for the 1 nanometer. Same goes for the MOSFET like CNT FET, but there is a catch. The ID of the Schottky barrier CNT FET gets saturated at 0.525 volts, whereas the ID of the MOSFET like CNT FET saturates at 0.42 volts. And another thing worth noticing here is the ID of the MOSFET like CNT FET is much greater than the Schottky barrier CNT FETs when the T oxide is 1 nanometers. Okay, so to specify it from the curve, we can see that it's nearly halfway through 1.25 to 1.5, while here in the MOSFET like CNT FET it's located halfway from 3 into 10 inverse 5 to 3.5 into 10 inverse 5. So Schottky barrier CNT FET should be avoided for the complementary application as much as possible. Well, in this slide, I am again discussing about the current voltage characteristics of the both CNT FETs by changing the chirality and temperature. The parameters that I have kept constant are the insulator thickness, dielectric constant, and the VDS and VGS, whereas the parameters that I have varied are the zigzag tubes versions and the temperatures. 11.0, 17.0, and 22 zigzag tubes were analyzed in the CNT FET lab. However, I have a plan to look for other simulators in later futures. Using those simulators, I will simulate further these CNT FETs, and then the temperatures at 200 Kelvin and 400 Kelvin were used to check how these two CNT FETs perform. This diagram shows both the SB FET and MOSFET like CNT all together. Then the second diagram shows that by changing the temperatures, the current is much higher for the MOSFET like CNT and the SB CNT in here is much lower compared to its counterpart. So the last line shows that the IDM CNT is much greater as of the 1100 TLT and 200 Kelvin. So yes, that's that. The MOSFET like CNT should be chosen at any cost. Before we stretch the conclusion of which one is the most preferable one, I would like to demonstrate you the modification of the dielectric constant which leads to the current voltage characteristics of these two CNT FETs. This table demonstrates you the dielectric materials that I have chosen for this project specifically. They are the silicon dioxide of dielectric constant of 3.9, silicon nitride of 7, hafnium silicon dioxide of 11, and zirconium of 25. The constant parameters were as it is. This curve shows you the Schottky barrier, CNT FET and MOSFET like CNT FET's performance when changing the dielectric constant. It is evident from this figure that at K is equal to 25, doped CNT FET, that is the MOSFET like CNT FET, has the highest current ID of around 3.75 into 10 inverse 5, whereas the undoped one or the SB CNT FET confines its drain current level at 3.54 into 10 inverse 5. Yes, that proves that the MOSFET like CNT FET is the perfect candidate to replace the Schottky barrier CNT FET. After all of these simulation results, I would like to finally state that every parameter changing effect delineates the fact that the MOSFET like CNT FET could be an ideal candidate to replace Schottky barrier CNT FET at any cost. That's all from my side. Now I would like to conclude my presentation here, and thanks for your patience.